Welcome to another video explaining the universe using the particle model. Well, today's video is a series of videos on equations, and this is a particular one using a DC signal with an RL load, emphasizing the inductor. But before we get into that topic, I would like to talk a little bit about the book we just released. And yes, the book we just released in August of this year is titled Principia Mathematica II, and it is available on Amazon. You can go to amazon.com/author/B.D. Hilster, and you'll get it to it directly. It is on sale in paperback in full color for $34.99 or on ebook for $2.99. You can also go to amazon.com/books/ and search for Principia Mathematica II, and you'll get that, our book, and many other books similarly titled. So, as I've been going through words in general, and one of the viewers asked about equations, and yeah, I've been doing a lot of equations. And these are previous videos I did on an equation. Here I did it on charge, and this is the one using DC signal with RL load. I'm in the process of doing an RL calculation. It's tough. But you're going to learn about the equations to do that, and that won't probably be my next one. Actually, my next one is probably going to be on the transformer. Okay, here's the standard explanation for a RL circuit. There's a DC battery, a switch to throw the switch up, and the current flows around, and it sets up and it generates in the magnetic field around the coil. These are all the standard equations, and I noticed he got this wrong. The time constant for the circuit is not R over L, it's L over R. And these are the voltages that you'll see across it. As soon as you close the switch up to A, you'll get an immediate 10 volt, this is based on having 10 volts, drop across the inductor, and you have nothing across the resistor. As the time goes on, and this one-time constant here, 2, 3, 4, as it builds up in charges, it charges less and less and less and less until it's full. That it's full, and at the same time, the voltage across the resistor goes up and up, such that when you add this point to this point, you get 10 volts. When you add this point to this point, you get 10 volts. You have to have a constant. If this adds 10 volts, this has got to drop 10 volts. This is the standard one, and they explain it. This is the explanation. They use equations to explain it. Well, here's a magnetic field here's an inductor with no magnetic field. And I've made this comment before, all components have a F2 force field around them, including me, including my computer, whatever. And I show that here's the inductor, and it's all the way around, not just 2 dimensions, but in 3 dimensions. But are generally able to analyze what's happening in just 2 dimensions. When the inductor has no magnetic field, the strength of the force field is based on the G2 mass of the inductor, and it's weak, or it's small, because the only only mass you have is the copper wire. G2 mass is a different mass. It's not in kilograms. G1 mass is in kilograms. There is no standard for G2 mass. Although I'm attempting a generalized version of G2 mass. So I said there's no standard unit of mass for G2 gravity. So I'm going to assume that 1 G1 will be used as 1 unit of G2 mass. 1 G1 particle, that's a G1 is like an electron with no charge moving at speed c, okay? And I'm going to assume that that's 1 unit of mass. The G2 particle interacts gravitationally with G1s and N1s of any atom, any level 1 atom. And so G2 is a lower level gravity that actually controls the flow of the G1 around the N1. And as an example of how many, what unit mass of a copper atom is, a copper has 29 G1s in orbit and 64 N1s in the nucleus. An N1 is about 2,000 times the size of a G1. Therefore, 64 times 2,000 is 128,000 plus the 29. So this is an equivalent 128,029 units of G2 mass, and the unit is based on 1 G1. It's a hypothetical unit. No measurements being made here. Everything's being measured in terms of that mass. I'm going to use the term for G2 mass of the inductor is mass of the inductor. L is the symbol for inductor. Well, now we go with an inductor with a magnetic field. When the inductor is charged, and I use that statement, it's a different kind of charging than a capacitor charge. This is the charge is the flow of G1s around and through the inductor, just like around and through a magnet. So when the inductor is charged, there are many G1s flowing through the inductor and many G1s stored in the magnetic field. This increases the G2 mass of the inductor. Remember, I'm saying now this force is stronger because not only do I have G1s flowing through, you accumulate over 5 time constants. You accumulate and completely fill this with as many G1s as it'll take, and that increases the G2 mass. It's not only the inductor, it's the ones flowing through, and it's the ones in the magnetic field. Now there are 2 effects of the force of the F2 on an inductor. The first effect is speed, and this is the same effect that I used in a diode and a transistor. As the 2 vertical forces increase, now we're talking about if you go from uncharged to charge, the G2 mass increases and the F2 force increases as the 2 vertical F2 forces increase. Talking about this one here, the average speed through the copper coil inductor increases, so G1s pass through more easily. Just like I said, it happens in the diode and the transistor. The pushing force, there is a pushing force. The horizontal forces this way keeps the G1s from escaping. In other words, every time it flows through here, most of them go through, some of them try to escape and get into the magnetic field. But the stronger this force is, the more they're held into the coil. Therefore, when fully charged, most, if not all of the G1s entering the inductor, most of them, when fully charged, most of them pass right through. If all of them pass through, then you have the same number out as in, then there's none lost. That means no voltage drop. And that's what you see at the end of that curve as it goes down. So when fully charged, there's none lost. There's none lost to the magnetic field or even randomly lost. Most of them go through. So this is, I'm repeating this diagram in this circuit, and here's a typical example of the battery being 10 volts, the resistor 1 kilo ohms, and the inductor 1 millihenry. And that gives a time constant of L over R, actually, of 1 second. So this is all the way out to 8 seconds. It takes 8 seconds for this inductor to get fully charged. Did you see when it's fully charged, there's no voltage drop? Why? Because all of them pass through due to the F2 force. Well, now that I'm getting into the equations, and I don't know any other way to do it. And if you're not interested in equations, you've got the part of the theory of the inductor, but I'm going to go ahead. The number of G1s being stored is the number of G1s trying to escape. They're trying to escape, reduced by the strength of the F2 force. The number trying to escape is equal to the number entering, which is B. That's a label in the diagram that I had, I didn't point it out, times the interaction factor of the inductor, IFL, times the inductance, which is L. So the number trying to escape is equal to the number entering the coil, an interaction factor. Now, I don't know what that number is yet. Don't have any real value. This is part of my problem in trying to do a calculation for this is I have to kind of play around with some of these numbers that I don't know what they are and see if I can get a right combination. The inductor is 1 millihenry. So the number, but then the number of lost in the resistor is similar. You notice this is a similar, the number of G1s entering the resistor is C, the interaction factor for the resistor is IFR, and resistance is in kilo, and this is 1 kilo ohm in our example. Again, I do not know what this value is. I got to play around with it. Although I do have a bit of a handle on this one from my DC work. The number trying to escape is reduced by this. See, this is the number trying to escape, BIFLL, and it's going to be reduced. So how does that happen? Well, it's based on the strength of the G2 force. So what in the world is the strength of the G2 force? The strength of the G2 force around an inductor is proportional to the G2 mass of the inductor plus the number of G1s flowing through the inductor plus the number of G1s stored in the magnetic field. This should be TS, not NS. So therefore, the strength of the F2 strength is proportional to the mass, G2 mass of the inductor, the number of G1s, because that adds, the G1s are the basic unit now of G2 mass, the number of ones entering, and the total stored in the magnetic field at any point in time. It's equal to this plus this plus this, and therefore we can use this this mass as a way of saying how strong is it at the beginning, how much stronger is it later, and that in fact is what I do here. This is the F2 reduction. The number trying to escape is reduced by the following factor, reduction factor. Now, there's no good way to go about this equation. It's just trial and error. You try it one way, you try it another way. But once you get it, it's fairly easy to understand. Let's assume we have our inductor is not charged. If it's not charged, then there's no G1s coming into it. B is the number of G1s coming in. There's none stored. So these two are zero at the beginning before you close the switch. B is 0, TS is 0, which makes this one, this is the mass, G2 mass of the inductor, and this is G2 mass. So the reduction factor is 1, which means at the very beginning, the force isn't strong enough to prevent charging. It's But as you increase these two and it gets larger and larger and larger, this becomes very large, and this is a small part of that large number. Now it's very small, and so our reduction force is high. It's low, but it prevents these from escaping, because the reduction factor being 0 is going to be 0 times the number entering. It's going to say, well, yeah, you're not going to store any. So this seems valid, but it's an empirical equations gotten through logic. And again, ML is the G2 mass of the inductor, B is the number of G1s entering, and TS is the number stored. Okay, number being stored and the number passing through. Number being stored, NBS, is the number trying to escape times the reduction factor. So the number being stored is the number trying to escape times that reduction factor. So this is the equation for the number trying to get out. And this is the reduction factor, prohibiting them at the beginning. It lets them all through, all being stored. And as this ML over a very large number gets close to 0, almost none are stored. A large number stored at the beginning, a small number stored at the end. And in the calculation, you've got to keep track of the total stored, and that's by adding every cycle. You get a number being stored, and you put it in the, you store it in a location. The next time you add it to, you keep adding. This is a running sum of the individual ones being stored in each cycle. The number passing through the inductor C is the number leaving the inductor going to the resistor, is the number entering B minus the number being stored, and so C is equal to this. So these are equations I've developed, and I'm using them in a spreadsheet. Okay, this is the whole one. I didn't go over all of it, but let's start with the equation for B. I usually start, you start with assuming what A is, but if the switch is open, A is 0. So the first time you get it, A is 0, and B is only equal to what the battery puts out. This is the voltage. If this is a 10-volt battery and the VG1 is 0.1 volts per G1, then this is 100. But that's the equation. B is equal to A plus what the battery puts out. B comes in here, into here, and so we're going to calculate what C is. C is B minus the number being stored, and the number being stored is that same long equation I showed you. D is equal to the number going in minus the number lost through the resistor. I showed you this earlier. And so you get D. That's the cycle. That when you calculate D, that's the end. And now when you start the next cycle, you make A equal to the A of the next cycle is equal to the D of the previous cycle. That represents one line. This represents one line in the spreadsheet. This represents how you start the next line, and you go through the same equations over again. Well, calculations I'm working on it. My next video, I would love to show you the calculations and show you that I can generate those two curves that I showed at the beginning. The voltage curve that goes up and the coil inductor that goes down. I'm not very confident I'm going to get there. There's multiple values I don't know, and I've recently come up with a method to try to home in on that, but I haven't done that yet. But very logically, I'll do the transformer next because it's very much related to the inductor. My name is Bob D. Hilster, and I am your particle model guru. If you have a question, ask Particle, and you can do that by going to particleguru@gmail.com, or when you watch a video, there's a bell up in the upper right. There's a little bell. You click on that, and you can type a little comment or question. Thank you for your attention.